All right, we are on the last section of chapter 1, section 1.3, describing quantitative data with numbers. So, some learning targets, we're going to calculate the measures of center, which are mean and median for a distribution, calculate and interpret measures of variability, which is range, standard deviation, and IQR, explain how outliers and skewness affect measures of center and variability, identify how outliers using the 1.5 times IQR rule, make and interpret box plots, and then use box plots and numerical summaries to compare distributions of quantitative data. So this is a direct next step of 1.2 where we talked a lot about the shape, but then we also mentioned the center, the spread, or the variability and outliers. Now we're actually going to quantify them, and we're going to talk about what we can use, what statistics we can use to describe them actually. So the first measure of center, there's a couple numbers we can use to describe the center. The first one is the mean. The mean of a distribution of quantitative data is the average of all the individual data values. To find the mean, add all the values and divide by the total number of observations. Our mean is no different than what we normally would trying to find the average like we have for most of our lives. This is just some notation. So if there's n number of objects, then we would say like x1 is like the first object, and then x2 dot 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 all the way to xn. If you ever have a long list of things in stats and generally in most math, the agreed upon way to describe it is the first observation, comma, the second, comma, dot, 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 comma, the last one. All right. We will often call, instead of saying the mean, we'll call it the x bar, which is the sample mean. We'll talk more about that here in a second. But it's x with a bar on top, and it's just pronounced bar. And it's given by this formula. Add up all the numbers, divide by n. Another way you might see it is this big sigma, capital sigma, means summation, so it means add, and you're going to add xi, so you're going to add x1 plus x2 plus x3, dot, 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 all the way to the last one, and divide by the number of data values. Again, we should be familiar with this, but this is just some formality, language, and notation for you all. So if we had that list of numbers again of the goals the U.S. women's soccer team scored in 2016, you would add them all up and then divide by 20, and the average or the mean comes out to 3.15 goals. So if we plotted that on we have our dot plot here, we see our average right here is 3.15. Another way to measure the center is the symbol x bar, I said, refers to the mean of a sample. And the notation mu, this is the Greek letter mu. If you've taken physics so far, you may be familiar with that coefficient of friction. But mu in stats is the mean of the population. So this is where the first bit of real, maybe new notation is super important here. A statistic is some way to calculate something about the sample. Okay, a statistic always goes with sample, so S and S. A parameter goes with the population, so P and P. So a statistic is a number that describes some characteristic of a sample. A parameter is a number that describes some characteristic of a population. So if you have a sample and you take the mean, you are using X bar. If you have a population and you take the mean, that is now mu. Okay, it is super important to know the difference between a statistic and a parameter, and therefore when you use X bar or mu. All right, if you write X bar is 3.15, but it's really a population, so it should be a parameter, and it should have been mu, you will lose points there. So it's super important to know, is this X bar or is this mu? And the way you know is, am I talking about a statistic or a parameter? And the way to know that is, am I having a sample or a population? So sample, X bar, population, mu. So here's the mean number of goals scored in 2016. If we exclude the games that are possible outliers, so that 9 and 10, and we see now that our X bar or our sample mean goes down to 2.44. All right. So what does this mean? It means that mean is not resistant. Okay, this word resistant in stats means that it's resistant to extreme values. So basically, if you add extreme values, it doesn't change that statistic or parameter. But for mean, we can see that, hey, if I took out those two extreme values at 9 and 10, that it really does change my mean by zero point 0.5 almost. So it is not resistant. Mean is not resistant. So here's another caution, just if you didn't hear me say it 5 times. The mean is sensitive to extreme values in the distribution, so therefore the mean is not a resistant measure of center. The second way to describe mean, or not mean, center is the median. So the median is the midpoint of a distribution, the number such that about half the observations are smaller and about half are larger. To find the median, arrange the data from smallest to largest, and then you kind of just go and find the middle. If the number if the number of data values is odd, the median will fall right in the middle. If it is even, you'll get two numbers and you just take the average. All right. So here's some raw data we have. So you can see it's not in um, smallest to largest order. So we're going to sort the data first, and then I would all right, I'm going to cancel out 21.5, cancel out the largest one, cancel out 21.9, cancel out 22.9, and I just keep canceling out smallest to largest until I find the middle number, which here would be 22.4. Again, this should be pretty familiar. We've probably been finding the mean the median our whole life, so it's no different here. Just to be aware that if it is an even number of data, so if you get like two numbers in between, you just take the average of those two. So here's the women's soccer team, boom, sorted, and we're between 2 and 2. So since these are the two numbers, that because it's even, we'll find the average, we'll add them up, 2 plus 2, and then divide by how many numbers there are. There's 2 data points, and we get our median is 2. So um, we'll see this in a little bit, but just because of the nature of this, the median is resistant, right? Because we're getting rid of the large values. It doesn't matter if they scored 10 goals. If they scored 15 even, right off the bat, we're going to cancel it off right away. And it's not going to change all these other numbers. We're still going to get the same median of 2.2. So that therefore the median is a resistant outlier, is resistant to extreme values. It is a resistant variable, right? So here's just to compare mean and median. If the distribution is roughly symmetric, the mean and median are going to be about equal, if not guaranteed to be equal. All right, so if it's roughly symmetric, they're going to be about equal. If they're skewed, the mean is going to get pulled towards that skewness, and that makes sense because the mean is not resistant. All right, large values, either big or small, but values that are far away from most of the data, the mean is going to get pulled towards it. So here we're skewed left, so that mean you see gets pulled closer to those extreme values. If I'm skewed right, again, that mean gets pulled towards those extreme values. So when looking at mean and median, that is another way to kind of help you decide the shape of the distribution. Is it skewed left, skewed right, or symmetric? If they're equal, it's going to be symmetric. If the mean is less than the median, it's skewed left. If the mean is greater than the median, it's skewed right. Now, I don't have that memorized in my head. I just think about what's going on here. Well, I know the mean gets pulled towards those outliers. So if it's skewed left, boom, my mean should be less than my median. And if I'm skewed right, it's going to get pulled to the greater values. So my mean should be greater than the median. And like I said, that's just another way in my head I check to make sure my skewness is correct. So this is exactly what I just said, but we'll go through it for you all. If a distribution of quantitative data is roughly symmetric and has no outliers, the mean and median will be similar. If the distribution is strongly skewed, the mean will be pulled in the direction of the skewness, but the median won't. For a right skewed distribution, we expect the mean to be greater than the median. For left skewed, we expect it to be less than the median. And like I said, the median is resistant to outliers, but the mean is not. Just a caution that I added in here. If you are asked to choose between mean and median as a measure of center, be sure to justify your choice based on the shape of the distribution. So if you know it's skewed, you should use median, not mean, because you know that mean is going to be skewed and get pulled towards those extreme values. All right. So talked a lot about the center here. And here's two distributions, distribution A and distribution B. And you could see, hey, their centers are going to be the same here. They're both right around 600. All right. But obviously, and they're both kind of symmetric. So if you just looked at center and shape, you would say these two distributions are the same. And that's why variability is very important, because variability tells us something different. You can obviously see here that the variability of B is greater than the variability of A. It's a lot more spread out for B than A. Center and shape do not do everything. That's why we need all four of those pieces when we're describing a distribution. All right. So a couple ways to describe variability. We talked about center is mean and median. For variability, the first one is going to be the range. The range of the distribution is the distance between the minimum value and the maximum value. So we just do max minus min. All right, we should be familiar with it. So you can see, hey, the max was 10 goals scored and the min was 1. So 10 minus 1 is 9 goals. Now, this caution is where so many people make this mistake. And so I will tell you this up until the AP test. But the range of a data set is a number. It is not you do not say, hey, the range of the data set is 10 to 1 or 1 to 10. That is not what range is. Range is a singular number, and it tells you how spread out it is. It is the distance from max to min. So it will be the range is 9 goals. All right. It is never an interval. Never an interval. All right. It is a singular number. Also, it should be. I don't like to use the word obvious in math, um, but sometimes I forget and I do say it. But it should be. We should be able to reason pretty clearly that the range is not resistant, right? If I added in, say they scored 15 goals in one game, that is going to change the range, because 15 minus 1 now is 14, significantly changes the range. So range is not a resistant measure of variability. Right? The second one, and this may be the first new one to describe today, but another measure of variability that we'll use pretty often is standard deviation. The standard deviation measures the typical distance of the values in a distribution from the mean. And I would write that down, and I'm going to say it again. The standard deviation measures the typical distance of the values in a distribution from the mean. I would be that almost, if it doesn't come up on our test, it comes up on the AP test. They might even just ask, hey, what's the definition of standard deviation? And you need to know it. It's the typical distance a value is from the mean. So how to calculate it, it's kind of a pain in the butt. You guys should be very happy about how we teach stats here. When I took stats at my high school, they made me calculate this all by hand, and then they showed us on the calculator how to do it. But we'll jump right into some calculator steps to help us. But it's good to know the formula and know how to calculate by hand, just so you kind of understand what's going on behind the scenes. So first thing first, it's a typical distance from the mean. So standard deviation and mean are very tightly related, you can say. So you have to find the mean first. And then standard deviation, or the word in there is deviate, or so that's like how far, like think about like you deviate on the path, you go away, you go off of it. So to calculate the deviation, you're going to take the x bar, or the x value minus the mean of each value in the mean. You will then square it. The reason why we square it is so that if you take the difference, some are going to be positive, some are going to be negative, and if you added those all up, it would come out to be 0. So we have to square it, add them all up, and then here we actually divide by n minus 1. Okay, that gives us the sample variance, and then you take the square root. All right, so this is the very ugly formula, but all it means is, hey, take the first x minus x bar, square it, plus x2 minus the mean, square it, plus x3 minus the mean, square it, plus dot dot dot, plus the last one minus the mean, square it. Once you've added that all up, you're going to divide by n minus 1, and then you're going to take the square root. All right. If you don't have the square root, that's the sample variance. Take the square root, it's the sample standard deviation. So knowing standard deviation, you should be able to find the variance very easily. You just square it and vice versa. So we can go ahead and do it with this small group of data just to calculate it. So first we find the mean, you add them all up, divide by 11 because there's 11 close friends, and you get a sample mean of 3. Calculate the deviation of each value of the mean. 1 minus 3 is -2, 2 minus 3 is -1, 3 minus 3 is -1, all the way down. You are then going to square those values and add them together to get 18. And then you divide by n minus 1. So here we'll divide by 10 because there's 11 data points. And that would be my variance, my sample variance. And then you take the square root and you get your standard deviation. And this is a sample, so we use sample standard deviation and we denote it by S sub x. So the same way mean is x bar for a sample and mu is the population mean, S sub x is the sample standard deviation. And we'll see, I don't know if we'll see it here in the future, but lowercase sigma is the population standard deviation. So, some properties of standard deviation, S sub x is always greater than or equal to 0. If it has a standard deviation of 0, that means that the typical distance from the mean is 0, which means that every point falls on the mean. It would mean that we had a uniform distribution. Not just that, it means that every value is the mean. Large values of S sub x indicate greater variation. S sub x, or the sample standard deviation, is not resistant to measure variability. It uses the mean, which is also not resistant, so that's why S sub x is also not. And like I said, the sample standard deviation measures the variation about the mean. So you go the mean and you go. So like this one where it says like 1.34. So you find the mean, and on at the typical point is going to be about 1.34 away from that mean. All right, that's where you'd expect the typical person to fall. All right. The third measure for variability, so we had range and then we had standard deviation. The third one is going to be the interquartile range, or what we call IQR. The quartiles of a distribution divide the order into 4 groups, right? Quartiles, you hear that word like quarter in it. So you split into 4 groups that have roughly the same number of values. To find the quartiles, arrange the data values from smallest to largest and find the median. So same way for the first thing to do, standard deviation, you found the mean. For IQR, you're going to find the median. Boom, and we split it up there. Then you're just going to find the median to the left of that and the median to the right. So you're going to find the middle value of these data points and the middle value of those. So the middle value to the left, that's going to be our first quartile. And then the third quartile is the median of the data to the right. So I like cancel. I'm between 22 and 25. But add those up. Not doing quick math right now. 22 plus 25 divided by 2 would be 23.5. So my Q1 would be 23.5, and then Q3 is what is that? Probably like 32.5 or something around there. And now you can see my quartiles have split up into 4 even groups. I got 3 data points, 3 data points, 3 data points, and 3 data points. So it splits them up into equal sections. The IQR, or interquartile range, is just the distance between the first and the third quartile. So just like range is from min to max, IQR is Q3 minus Q1. And IQR follows the same thing that range does. It is not an interval, it is a singular number. So here, I think it's 32.5. So our IQR is 9 here. So here's some other data. It's the time travels for 20 New Yorkers. So you first put in order from smallest to largest, and then you find the median, which is right here, and then split it up again. Get your Q1, Q3. Boom. Find IQR 42.5 minus 15, which is 27.5 minutes. Again, like I said, make sure you say that it is a singular number and not an interval. All right. So the range of the middle half of the time travel for New Yorkers in the sample is 27.5. That's how you can. Right? Now, because you're looking at just the middle, kind of, IQR is going to be resistant to large values, right? Because those large values don't really influence it because you're looking at kind of the middle. Um, so it cancels out any of those extreme values. So IQR is going to be resistant. Right? Now, yesterday or in the last video, we just talked about how you could look at the data and see, hey, that might be an outlier. That value seems pretty high. From now on, we will actually have a number to justify outliers, and it's 1.5 times the IQR. So first, you get the IQR, and then you're going to times it by 1.5, and then if there's any numbers lower than that, let's just an example. I think the words kind of mix it up a little bit. So we got some data here, plotted out. Q1 is 22.2, and Q3 is 22.6. So you find the IQR range, 22.6, boom, minus 22.2, 0.4. So now we're going to times it by 1.5, and this is kind of our key. So we're 0.6. So there's any data less than Q1, so Q1 minus IQR times 1.5, that's going to be an outlier. And there's any number greater than Q3 plus 1.5 times the IQR, that would be an outlier. So first things first, I'm going to take my Q1, 22.2, and I'm going to minus my 1.5 times IQR, which is 0.6. And I get 21.6. So if there's any number less than 21.6, it's going to be an outlier. And sure enough, boom, it is right there. So that is one outlier. I have to check the other way. My Q3 plus my outlier, 23.2. So if there's any number bigger than that, which there is, so that is also an outlier. All right. So this is the calculations I just showed on the calculator, but lower outliers are less than Q1 minus 1.5 times IQR. And high outliers are Q3 are greater than Q3 plus 1.5 times IQR. So those two are outliers. So why do you want to look for outliers? They might be inaccurate data values. Sometimes you just type data into your calculator wrong, or you obtain the data incorrectly. So it's good to notice, hey, this might be a wrong data point. If everything is correct, it could just be a remarkable occurrence or some other thing, some other noteworthy piece, like, hey, like maybe that person is just extremely fast here or extremely slow. And the reason why it's super important is they can have heavy influence on the values of some of our summary statistics, right? Those things that are not resistant, like mean, range, standard deviation, can get heavily pulled by those outliers. So it's important to know if there are any outliers there to see how much that mean, range, or standard deviation is being pulled. Right. Next important thing, it's called a 5-number summary. This is a pretty common multiple choice question where they'll just give you a group of data and say, hey, what's a 5-number summary, and in a specific order. So the 5-number summary is always, and it is always in this order, the minimum, comma, the first Q1, comma, the median, comma, Q3, comma, the maximum. It's always 5-number summary in that order. So here's the data to see. So min, Q1, median, Q3, max. All right. To find it on the calculator, I've already typed this data in, and don't worry too much, but we'll get a lot of practice at it. But if you go to stat and edit, and say you put all the data in of all these data points, which I've already done before, so you don't have to watch me painfully type things away. Ooh, that's not what I want. I really hope that doesn't mess anything up. Go to stat, edit. I think we're good. Okay, go to then if you go to stat, calc, one var stat, press enter, you get all the data. You get the mean or x bar. You get how many data points there are. You get S sub x, that sample standard deviation is 0.37. But if you come down, you get the 5-number summary. So you get min is 21.5, Q1 is 22.2, median is 22.4, Q3 is 22.6, and 23.3 is the max. So if you type the data into your calculator, it will right away calculate that 5-number summary for you. To make a box plot, the box plot is basically just a visual representation of the 5-number summary. So we're just gonna keep going. So if you have your horizontal axis, you drop in your Q1 and Q3 as the box, and then that middle line is the median, and then you draw some whiskers out. So the whiskers extend towards the last value that are not an outlier. So here you can see that we know we have a data point over here. So it doesn't quite go to the min because there's outliers, and they get marked as asterisks. All right. So these asterisks are our min and our max, and then this would be the last data point that's not an outlier. The important thing about box plots to remember is they do not display each individual value in a distribution, and box plots don't show gaps, clusters, or peaks, so they don't do the best. Like I said, they really are just a visual representation of the 5-number summary, but they still do a pretty good job to help us out with that. To see how to make it on the calculator, I'm going to take that same data, and we'll practice this a lot, but feel like your y equals, this is where you normally type in your equations, but we're in stats, I'm not typing an equation in. So instead, I'm going to do second y equals, and it gets me to this kind of, the plot, so you can say. I'm going to press enter. I have on or off. I want to turn the first one on, and then down here is my option. So this is kind of like you got some options here. This first one would be, what is this called? Well, it could be a dot plot, but it's more so a, why can't I think of the word? I don't know. It's where like your x values would be on the x-axis and your y values would be on the y-axis. I can't think of the name of it is right now, off the top of my head. That's okay. This would be a histogram. This would be, in here we see two. These are both box plots. So here's one and here's one. You can see how this first one has dots in it. I'm going to table off so you can see it. So there's a couple dots in it, and this one has no dots. We use this one with the dots because it will show us if there's any outliers or not. So click on that. My data is in L1 and my frequency is 1. So now I want to graph it. So I'm just going to go zoom. And if I table down to zoom stat, which is 9, it's going to show me the box plot. So zoom 9. All right. Let's try something out here. Let's turn the second one on. And this time I'm going to do the secondary box plot. All right. Let's see if we can graph it. So the top one is a box plot with the little dots, and the one below it is just the regular box plot on the calculator. And you can see that they are exactly the same. The only difference is instead of this bottom one doesn't show outliers. It just goes from the min to the max. The top one tells you, hey, if this line doesn't go all the way to the minimum value, that minimum value is an outlier. All right. So that's why on our calculators, we always want to use this box plot that has the little dots on it, because it will automatically calculate outliers using that 1.5 times IQR rule. All right. So that's why it's important. And that's kind of how the calculator does it. Either way, though, min, Q1, Q median, Q3, and then maximum. Be careful that if you're using this box plot on top, that you don't say this is the median or this is Q1 or this is the minimum value or Q1. That's just the next smallest value. Our min is still that outlier. Our Q1, median, Q3, and maximum. I put extra AP exam tip in there. So using statistical terms carefully and correctly on the AP statistics exam is extremely important. Don't say mean if you really mean median. Range is a singular number, and so are Q1, Q3, and IQR. Don't use it is the interval from blank to blank. You will lose points. All right. Avoid poor use of language like the outlier skews the mean or the median is in the middle of the IQR. Skewed is a shape, and the IQR is a singular number, not a region. So just be very particular in the terms you use, or else you could lose credit. Um, and only use outliers. You can say you suspect there might be an outlier, but now that you know the rule, just go and calculate if it's an outlier or not. And if it's not an outlier, don't call it an outlier, even if it's very far away. Now that you know it's 1.5 times IQR, you can calculate if something's an outlier or not. And only then should you say, hey, this is an outlier. Huh? So that's it for today. Here's the learning target. So we calculate the measures of center, which is mean and median. We calculate and interpret the measures of variability, which is range, standard deviation, IQR. Explain how outliers and skewness affect the measure of center variability. Identify outliers using 1.5 times IQR rule. Make and interpret box plots for quantitative data. And use box plots and numerical summaries to compare distributions of quantitative data. All right.